My name is Wenda. I'm with Bytedance. So unfortunately, Jay would not manage to come due to the traffic jam. So I will try to cover his part as much as possible. So today's topic is about the load balancing and optimal path utilization. So we are targeting building GPU clusters for AI application, as many of you can imagine. So the problem we see with the AI fabric is the load balancing. So this is the core topic of today. So in the traditional path selection, we can see that the next hop selection is mostly static, either based on the static hashing of ECMP or WECMP. So the link state will mostly based on the link up and down, with some bandwidth information in the weighted ECMP. So so it doesn't cover the link quality. So most recently we have the ARS definition in the side spec, and it doesn't cover the remote link downstream the path. So so for the control plane, I think the BGP convergence is slow, so it mostly provides the connectivity, and has the potential to add bandwidth information there, but the convergence time is slow, so it probably will not adapt to the changing traffic. So so our question here is, can we do a better path selection? So the first step, I think, is the monitor of the local link quality, and then we took one step forward is to account for the remote quality. So with that global information, we believe that we can achieve better load balancing and further the better performance in application. So so we actually building AI fabric for various scales of GPU clusters. So depending on the application, our cluster can have GPUs from 1K to up to 128Ks. So larger scale GPUs will require more tiers into the fabric. So we started from 2 tiers, and it will grow into 3 tiers and even 4 tiers with the growth in GPU scale. So despite these variations in topology, we use the same building blocks. One is the real optimized interconnection, and the other is the cross topology. So the communication between GPUs is based on the Rocky V2, and it requires a lossless fabric. So the lossless transmission is guaranteed by using the layer 2 PFC scheme. So the rest of the effort in building a better AI fabric is on providing better load balancing. So this is a showcase of a switching element. So we have R&D efforts in both hardware and software. So this is our latest white box that has the capability of 51.2T throughput. So it is designed for Tomahawk 5, as some of you may guess. So here is a front panel, is a front view that shows that it has 64 800G front panel port that support OSFP optical transmission. So we bring quite a few cutting edge technologies into the box. So most notably, all the ports, all the front panel ports will support the linear drive pluggable optics. And among other innovations will include the PCB design. So this work was published in last year DesignCom and also exhibited in OFC, but still it's a first time introduction to the OCP community. So at the software side, so we have in-house development based on the shoulder of Sonic, community Sonic. So I listed a few of these features here, and among other features. The first foremost is the enabling of ARS adaptive routing. So our development is on top of the SAI ARS specification. So we will detail some results in the next slide. The next is the IFA 2.0. So this is the target here is to develop a better congestion control algorithm for the end host. So it shares somehow the similar idea as the global load balancing. That is by providing better visibility into the quality along the path. So also this development is on top of the Psi 10 spec. Next, we improve the precision in traffic and congestion monitoring. So this is based on the sonic flash counter architecture that we managed to push the polling scale down to 1 second without performance hits to other CPU applications. Last but not least is the warm upgrade tool for the online bug fix. So our method is to adopt various hotfix techniques, including the community warm reboot, but not limited to it. So it can be think of as a framework that you can cherry pick the best suited tool for each individual bug. So now back to the load balancing. So we have actually started the deployment of ARS into our production. And we support 2 modes. One is the ARS flowlet mode, and the other is the packet spray, which in the formal term is called ARS per packet mode. So why we adopt 2 modes is to accommodate the AR capability at the host NIC side. So from the deployment, we do observe higher throughput and a faster link failure over from the fabric perspective by enabling the ARS. So we also measure the actual benefits to the AI application. This is via measuring the GPU internal bus bandwidth, as shown in the diagrams. So we do see a significant improvement over the GPU internal bus bandwidth by employing the ARS. And the exact numbers are listed here for typical AI traffic patterns. Now, so despite the significant improvement, we still see some gaps by using the ARS method. So because the ARS only monitors the local outgoing link, so it's not able to cope with remote quality changes down the packet path. So this will limit its load balancing capability under network scenarios where the remote link quality changes are involved. So we listed here 3 scenarios, and we will discuss in detail. One is the remote link congestion, remote link failure, and the multi-link scenario in the next slide. So actually, these are already these 3 scenarios are all addressed in our implementation. So now the first one is congestion. So now let's discuss based on the topology diagram here. So here we actually have all the building blocks we just mentioned. One is the rail optimized interconnection, and the other is the cross interconnect. So now, so here we also draw a flow between 2 top of rack switches. They are sitting in 2 different rails. So this is a typical flow of cross-rail communication. So now let's look at the a segment of the flow that the path that start from the spine switch sitting in the top tier down to the destination tool. So here the spine switch cannot select an optimal path when the remote link is congested. So the motivation is to balance load better. So the idea here is that we want the spine switch to take an alternative path that will bypass the congested link. Um, so, there from the current status, there are two enhancements that need to that will be introduced. One is that the awareness. So the spine switch need to be aware of the remote quality changes on the remote link. And the second is the modification to the cross-rail connectivity. So here, notice that this green link, it connects the spine switch to the rail. And typically, this green link will represent multiple links. And all these links now connected to one leaf switch within the rails. So the idea to create diverse passes is to distribute the link connected to multiple leaf switches within a rail, so that when the link congestion, the spine switch has the connectivity to forward the packets to an alternative path. I think in Jay's part, it has a diagram illustrating that there's a link here will connect to two leaf switches in the rail. So now let's move to the second scenario, the link failures. So this will further justifies the topological changes we just made. So here, now consider this remote link is failed. So from the connectivity perspective, the only point that would be able to take an alternative path that bypasses the link would start from the source tour here. So although this failure information can reach the source tour, it would take several hops to do so. So this would cause longer longer time in packet loss. So with the change here in cross-rail topology connectivity, then we can see that the spine switch in the middle will have the connectivity to take the alternative path. Then this will reduce the convergence hop and reduce the impact on failures. So the last one is the multi-link scenario. So we mentioned that for the connectivity between two adjacent switches that consists of multiple physical links that are operating at the same speed. So here we draw the two-hop path from leaf switch to leaf switch. So it consists of uplink path and the uplink hop and the downlink hop. So when the downlink fails here, so you can see it will create a link bottleneck here on the downlink hop. So it's another form of congestion. So so the idea is to eliminate the bottleneck. So our method is to have the leaf switch proactively remove one of the next hop group member along the path, so that the bandwidth on the uplink will have the match bandwidth on the downlink. So in doing so, that we can have consistent bandwidth all over the path. So, but first foremost, the leaf switch would need to know the link status on the remote side. So this is a similar requirement as the previous scenarios. We actually, so far we have discussed the three challenges and our way of addressing it. So now we talk a little bit about our implementation. So to summarize, so the whole idea is built around to account for the remote link quality in the local forwarding decision. So that will require enhancements in both control plane and data plane. So at the control plane, the remote quality need to be visible via control plane messages to the uplink node. So this update uh, need to be done at the microsecond level. So at this time scale, the regular routing protocols currently in action will not be able to taken as a vehicle to deliver such messages. So next, once the switch has this information, it needs to sync this information to the data plane. So there are various ways in ASIC design to do so. So here we illustrate one of them by using the hierarchical ECMP, which is also defined in the side spec, that we would attach the remote innovation in the layer 1 next hop group and then let it propagate along the pipeline to the layer 2 group, which is ARS enabled. Then the layer 2 next hop group will have the information of remote link quality to account for it in its forwarding decision. Um, so, so another point I want to make is that so here we based our discussion on the notion of um, downstream pass or pass. So it would be desirable to create one ARS-enabled ECM for each pass. So this is in contrast to the current situation deployment that multiple different leaf routes would typically point to one ARS-enabled next hop group. So so doing so would allow us the flexibility to manipulate the next hop group members. Yeah, so for the rest, for the other control plane modifications, we push to our proprietary protocol. So the idea behind it is to minimize the changes to BGP, so it will have the fundamental stability in our routing system. Next is the SI ARS enhancement. So I think the core idea here is to build on top of the current ARS definition that we bring in a new object called the ARS path profile here. It will have two types. One is the publisher, which is for the downstream node to monitor its quality, and a subscriber that is targeting the upstream node to listen to the quality changes. So I think here is the core idea. So when we look at this three-tier network, so for the Tor 1.0.0 node here, it would act as a subscriber, so it will listen to the remote quality update from the leaf switch here. Next is the leaf switch. So it has two roles. It will monitor the downlink to the tour and then distribute the quality to the rest of the tour. And also the up-facing link, it will monitor the quality of the spine switch and then distribute them to the rest of the spine switch, and it will also distribute it to the tour here. So last is the leaf. I think so. It has a similar role. So I will skip this part. Yeah. So we have in-house development, and we would like to push it to the community. That's all.